Okay. Let's continue. You can still see my screen and everything else. Hear the audio. Or not? Since okay, yes, we have right. That's great. Yes. So yes, this I guess we were talking about this view synchronous communication or view synchronous broadcast, and the idea here is that this will the view synchronous broadcast will message uh, ensures that message delivery is ordered with respect to installation of views. Um, so it so it gives the illusion, or it's maybe not correct word to use illusion, but the abstraction makes it so for the application layer that the failures are synchronized and they appear to happen atomically with delivered messages. So I have a sequence flow here. I'm not sure if this is. Let's see if I have some notes for this. Yes. So here it has two types of views. You can say it has a view synchronous view and group membership view, and this is kind of sliced through here with the lines here, and then we have the TRB terminating reliable broadcast, and they all capture all the messages seen. So these blocks here, they represent the messages seen by the different processes. So, for example, process Q, what messages has it seen? Well, it has seen M2 here and M3, and this is represented or written here. So we can see process S, it has M1 and M3, and this is also seen here. So then aggregated together, this is M1, M2, M3, and well, process P, it didn't see any messages, so it has this delta or nil value here. And yes, it's also crashed. So after this, they all know what messages they must deliver, and once they deliver these messages, they all move to the next view with the same messages delivered. So the algorithm, or well, the module description here, and now you see that we are beginning to have more of these involved algorithms here, because now we have 3 indication events and 2 request events. So what happens here? So the idea with the block, first off, that's to prevent, or it's a flow control mechanism to prevent, or to stop the problem of constantly moving to new views if messages are seen. So it kind of stops new messages from being broadcasted until the view is finished installed. So yes, the same properties as the reliable broadcast and the group membership, with the one added property, view inclusion. If some process delivers a message M from process P in view V, then M was broadcast by P in view V. So here it's talking about the view for the view synchronous communication, not the view for the group membership. So it can be a little bit confusing since they both use view. Anyway, this is the algorithm, and well, you can tell that it's quite involved just by looking at how long the pseudocode is. So I don't think that we need to go into the deep understanding of this particular algorithm, but still I would recommend for yourself to have a look on this this algorithm, and one thing to keep in mind is that you have two phases here, or two, yeah, let's say 2 phases, and so this is like the first phase here with everyone is allowed to broadcast, that you see different processes of broadcasting different messages. And then the next phase is the block phase, or they call it view change, I guess. Anyway, the point is that when there's a block, then the processes are not allowed to broadcast new messages. And you can see that here. So the application or the process is allowed to broadcast whenever blocked is set to false. So as long as blocked is set to false, it can include any message to the view and broadcast this message. And at some whenever there is let's say I need to change to a new view, then the blocking is set to true, and it cannot broadcast more messages. So you can see that here, when there's a block OK event, then the blocked flag is set to true, and we do not allow new messages to be broadcast. Yes. So I think that concludes this part here with the consensus variance, and there are no objections, then I wanted to move on to shared memory, and just I can bring up our lecture plan here. We have so now we will take this shared memory chapter. Right. So let's just get going with this. I will not take the whole thing today, but so the shared memory, we talk about this usually with using the abstraction registers, and this register abstraction, it captures read and write in distributed programming. And we have two types, the regular type and the atomic type. And today we will look at the regular, and on Monday we will finish off with the atomic part. So all of these shared memory abstractions, they are have mainly two operations: the read and write, and it's easy to know what they are. And we, as in all distributed algorithms, we want to ensure these two properties, liveness and safety, that every operation eventually completes. So it can be a long write or a long read, but eventually it will complete. And the safety property here is that every read returns the last written value. So one of the questions that we have here is, what is the last written value actually? And as you will see, it can be not always so clear. But we use this notation here. The first, like we have X, Y. So it's for X readers, or X writers and Y readers. And yeah, oftentimes you have yeah, let me correct that here before totally confusing. Yeah, oftentimes we have like one writer and then a lot of readers, so it kind of pub stub type of thing that only one process can write, but anyone can read, and more advanced registers has an NN, meaning anyone can read and write. Or you might have any combination of this depending on your specific application or need. Yeah. So what is this last written value? So consider we have this scenario here, and then everyone can see that this is very nice and easy. We have two processes, and one process is writing the value 5. Afterwards, the P1, it can read the value 5. Then the process 2 can write the value 6, and shortly after, the process 1 can read the value 6. So here we don't have any failures, and everything happens in a sequence. Just as you can imagine, this could be just on one process actually, but yeah, so everything happens nice and sequentially here. But what happens if you have this scenario that P2 first write value 5, and it starts to write the value 6, but it crashes before it completes fully. Then what is the correct value that the P1 should read? So should it return no value, or should it return the value 5 or the value 6? So what is the correct thing to do here? To answer this, we will see what happens in the algorithms. But this is just an illustration to show that why is this a challenge here. So just a few definitions. So we say that one operation, so an operation, yes, this is again a read or a write operation. It is complete if it did not crash before receiving confirmation. So yeah, you can think about this as after I read, a confirmation is that the value is replied back to the whoever initiated the read command, and for a write, a confirmation will be like an ACK or a confirmation, somehow a confirmation message. But yeah, the idea here is that it fully completes, and if it's not complete, then it's failed. So this happens when the process P crashes typically, and we also say that the operation A at P1 precede operation B at P2. Only it can only precede another one if it's complete, meaning that it's finished and it has sent a confirmation. And one last thing is that we say also that there is an operation or two operation can be sequential if one of them precedes the other one, and if they are not sequential, they must be concurrent. This is a bit similar to the cursor ordering that we saw before. So the first register that we have, it's one writer and n readers. So n readers, it usually means all the processes in the system. So any process can read, same thing. So this gives us strong guarantees of what values will be read if there are no concurrency or no failed operations. This is one similar like say a negative example where we don't have a regular register, or at least it's not working correctly, because here we have a value, a process P that has written the value X and it has completed, but somehow the process Q reads another value first, and only after a long time or a while it reads the value X, and also it reads the value Y before the value Y is written completely. So the last thing here, it's not necessarily wrong, but the first read here, it's not. It's wrong. And then we have another example with the same pattern that we have written two values X and Y, but the another process Q, it doesn't read the last value written, because the last value written, it is this Y, but it reads the X. So this is another problematic execution. The correct execution, it's here. So here we read the value X, and we read the value X even though, for example, here it reads the value X even though the write has started, but after it is near to complete, we read the value Y. So actually this last read here, it would be correct even if it was X here, because the write didn't finish. So the last read, it can be seen, or the argument of why it's correct. It's in this validity property of the regular registry module description, and it says a read that is not concurrent with the write returns the last value written. So remember, what reads are not concurrent with the write. So we have only actually one read that's not concurrent with the write. So these two here, they are concurrent. Or a read that is concurrent with the write returns the last value written or the value currently written. So that's why it's adhering to the specification of the module. But since we have the we have the or we have the or condition here, then it could have also returned X, and it would still be okay. So the pseudocode here, we will just take a look here. It's not so long, and you can see that we are using a perfect failure detector. We are using a best effort broadcast and perfect point-to-point links. So if you were to draw this module, then you would have to remember to include all those other modules. So what happens here? Okay, so here the ONRR, this is what is it? Yeah, 1N. So this is 1N regular register. So 1 ONN, this is 1N regular register. This is a fail stop algorithm, and each process has a local register, which they call val. So the writer updates all processes that are not crashed with a new value. So it whenever the application layer wants to write a value, this value is broadcasted to all the processes, and whenever another process receives this write, it adds it to its local registry and send an acknowledgement for that value. Whenever the acknowledgement is received, then that by a process, that process is added to the write set, and when the correct all the correct processes are in the write set, so that all the correct processes, they have delivered this acknowledgement, then we trigger this write return. So it means that now the value is written. So this returns back to the application layer, and you can see here that this write return, it means complete a write operation on the register. So now we have written the value to all the local registers of all the processes, all the correct processes. So this it's this type of algorithm. It's can be useful for applications where the read to write ratio is high, meaning that there is many more readers than writers in the system. All right. So that's what I wanted to say about that. Well, maybe just one more. So what So with the right set here, you see that we need to have this we need to have all the correct processes in the right set. So this can be improved upon or modified to take advantage of what we call a majority. So a majority will be more than half. So the idea here is that if we have a majority of more than half, then it's not possible to make another majority that doesn't have a correct process. So any two majorities, it must overlap in at least one process. So this majority voting regular register, it takes advantage of what we call witnesses, and these witnesses, they create from quorums or from the majorities. So this is captured with this read list set. So again, whenever we want to, the application wants to write the value, it's the value is broadcasted to all the processes, and yeah, the acknowledgement is sent, and just when we have more than half of the acknowledgement, then the write this the right return is written or is indicated to the application. And kind of similar for the read operation, we trigger a broadcast for a read operation. This is delivered to all the processes. Then they each of them sends the value with the perfect point-to-point link. And whenever we have more than a majority of witnesses, then we choose the highest value from this and return that value. And then after this, we in both cases, we before we return, we set the acknowledgement to 0 and the read list also to the 0 value. So, or we remove all the process from that set. So the idea is to not have duplicate returns sent. So consider the last process to send an ACK before we are over half, and if we didn't reset the counter here, then we would keep on sending or indicating the return value for any process over the majority that returned. Yes, okay. So that was the regular register, and I wanted to do the atomic registry on Monday. and on Monday, yeah, we will finish with the book. So I was wondering if there's anyone that needs to have another look at the Paxos pseudocode, or if it's clear. I didn't have any one of you telling me that I should or shouldn't. And well, the only as I said, there was one student that wanted some help with pseudocode, but yeah, I still didn't get. I don't know which particular pseudocode that I should repeat. And also with the lab 4, we now there's I think roughly 3 weeks until the deadline. So yes, on 15th March. If you encounter any problems, try to let us know early on, and then we can try to do something, help you. Otherwise, yes, we will finish chapter 4 on Monday, and then we will also start with this consistent global states. And please let me know regarding the labs if there are too much work for you, or because we have the plan to have paper presentations that each of you will present a paper, but I will not do this if you feel that you need the time to work on the labs. So I didn't have any message from anyone if you feel the workload is too high or not. And anonymous message is also fine. But yeah, so typically, students, they can wait until the last day to try to finish the lab, but it will not be so easy for you if you try to do that with this Paxos algorithm. So I recommend you to try to get starting on it as soon as possible, and let me or the TAs know if you need any assistance. And otherwise, yes, we will finish the book on Monday, then we will do another presentation or another apart from a different book concerning consistent global states. And then I had the plan to present some of Academia or code, and this well, it can be interesting for you in the sense that you can perhaps get some ideas for your own project, and the same with the blockchain presentation. But yeah, if there is no further questions, then I will end for today, and we will meet again on Monday. So I didn't have any questions, so I guess that you are satisfied. So okay, bye bye. See you on Monday.